Hello, welcome to session number 33 in the series Unlock Circuit Design using ADS. And for the past, I think the past one series was using Cadence. This one is also going to be using Cadence. And I wanted to talk to you regarding some important point of view. So what you see here, somebody forwarded me this respond basket 2022, and this is coming from ISRO. Now, the point I wanted to make is uh, this is like a, a program which they run with various academic institutions. And basically, that means is that they have a list of projects which they are going to send to various participants, which are the institutes, and various professors are going to pitch in for this kind of a funding. So this is usually a 3-year funding, and every year you can send them a budget, and under various heads you can charge, but you cannot charge for being for what you call principal investigator or a co-PI. That means that you have to be associated with the institute as a professor uh, to be able to pitch in for this project. And then your institute will be paid in terms of various budgets, right? Under various recurring or non-recurring heads. But the one who is working, the principal investigator, is not going to be paid, or co-principal investigator. Now, the onus of implementing this is going to come on to a junior or senior research fellow, and then you can ask for 2 or 3 junior or senior research fellow, and they're going to pay you 30,000 rupees to anywhere up to 40,000 rupees for this kind of a per month for this kind of a project. So now you can understand what kind of people who will be working as a junior or a senior research fellow, right? They must be students pursuing MTech or PhDs, right? So now this project, first of all, it's going to be handed to a professor who has to be employed with the institute. And if you are someone who are not employed with the institute for many personal reasons, and one basic personal reason is the politics, probably you cannot pitch in for this project, right? So being talented, you are basically shut out because of the politics in various colleges, right? Because you are not a professor there, right? Okay, so you have to be a professor to do this. Now, can a professor do it? Well, he is going to, maybe he can, maybe he cannot, but you have to, he will depend on those 30,000 worth of, talent, which is going to be MTech or a PhD, who can take 3 years to do this, right? And every year they can charge something like 40-50 lakhs, which is easy to go through without approval. Anything higher, they will need a special permission. But below that, that's what they told me. Below that, it's easy. So let's say this institute is given a project out of this list, and they are given 30,000 per junior research fellow, and then let's say 2-3 that, and then the rest is the budgeting in the form of infrastructure costs. But tell me this, okay? 3 years on a project which is mentioned over here under various centers, right? So this is a public information. This is not a private information. So I'm just sharing with you. And why I'm sharing with you? Because I have struggled 15 years with this organization trying to get a project. And the main hurdle has been, how would we pay you, right? So we can only pay you through Respond, and you understand what this kind of arrangement is. And as a consultant, we can't pay you, right? Because our administration wants the work to be done by our employees. We can get trainings from you, but then we cannot get consultancy from you. So that's what they have been telling me, right? So let's pick up a project. So I'm going to throw in a challenge to myself. So let's pick up this guy. Okay, so this is it says design and implementation of CAB and fractional and PLL based on tunable frequency synthesizer. And the co-PI from ISRO side is going to be Shri Anmaya, Anmalya Bhattacharya and Srimati Harshita Tolani. Right now, what they are expecting is a wideband tunable LO, which will be generating a frequency, and it has to be controlled by a fractional N and a integer N mode. So basically, fractional N means that your sigma delta is working, and if you disable sigma delta, then it's a fixed N, right? So that's there. And they are expecting to move them DXF PCB files. That means that you will not even design this. What you will do is you will buy off the shelf component, put them onto a board, and then supply it, right? And that you do over a period of 3 years, and that will be taking help of ME, MTech, PhD students under a professor, and professors are usually NITs or IITs, right? Okay, so this is there. So let's throw a challenge to myself, and the challenge to myself is, can I design this in 3 days? Okay, so what I'm trying to do is throwing a challenge to myself. I want to do this in 3 days, and they give 3 years to a professor with 2 or 3 research fellows, right? So let's just see how difficult it is to do this. Okay, so here is the loop filter, and this program I have written, I have used this in previous sessions also. For this particular session, I just punched in some VCO, tuning range, and voltages, right? So basically over here, I punched in 28.5 gigahertz and then 26.3 gigahertz. So basically this is a one of the bands. So I have to cover the entire band from 24.3 gigahertz up to 28.5 gigahertz. So I'm splitting the band into two. I'm splitting the band into two because such a broad band tuning range is not possible, right? So I'm splitting this tuning range from 24.3 to 26.5, and then 26.5 or 26.3 to 28.5. So basically there's slight overlapping between the bands. So I have dual band fractional and PLL to cover the entire range, and I'm going to use a crystal frequency of 40 megahertz, and I'll tell you why these choices are there, as I have done in previous sessions also, right? So if you look at the loop dynamics, what I have come across is this is the loop filter values, right? So basically these are my loop filter values here, right? So this is the loop filter values which I'm going to stick to, and here uh, the K phi is 1.3 milliamps of current, because I have split the band into two, and my tuning range on voltage is from 0.4 volts to 1.6 volts, right, from a supply of 1.8 volts. So I have this tuning range of 0.4 volts to 1.6 volts, and in this I'm able to achieve 2 gigahertz of band, right? So there is a 4 gigahertz of band which I have to address, so I'm splitting it into two. I'm going from 24.3 to 26.5, and 26.3 to 28.5. So the entire Ka band is covered. Now, this synthesizer can also be used for your 5G applications in Ka band, right? So I don't know what is the application for this particular organization, but this is for 5G in mind, right? So this is a Ka band synthesizer. Now 40 megahertz, let's do some maths. Okay, so let's say the sigma delta is 16 bits. So basically, first of all, let's say I'm pick one frequency, let's say 27,500 megahertz, right? So this frequency, first of all, it has to be divided by some injection lock divider, which I have used now in my 40 gigahertz PL. So same injection lock divider of divide by 8 I'm going to use. So this leaves me with this number. Now this number is a part of the loop, right? It's a multimodulus fractional and divider, which is 6-bit. So 6-bit divider means that you can go from 2 raised to 6, right? So 2 raised to 6 to 2 raised to 7 minus 1. So basically it can go from 64 to 127. right? So let's say if I divide this by 40, so I have 85. So basically it falls in the range of 64 to 127. So this is a 6-bit divider is sufficient for this. Again, I told you in my previous session that the fractional uh, the mesh 111 is going to generate 8 states from 0 to 7, right? So 7 as a percentage of the least count, which is 64, or 8 as a percentage of least count, which is 64, right? It's around 12% or 13%. So here what will happen is you will see you have to trade off with the loop gain, so as to have the flatness of the control voltage. So as I told you previously, your 8 count of 8 should be, less than 10%, but this is right 12.5%. So I'm sticking with the 6-bit. If I go to the 7-bit, I would have to increase the k-phi a lot. So almost like, I have to go up to 2 milliamps from the charge pump, right? So 2 milliamps of source and sink. That means that, I have to work with very large transistors to have the right swing, like, have to have a swing where the impedance of uh, these charge pump current mirrors is large for a large swing, right? So twice of overdrive is what you will have, uh, 2 VDD minus twice of overdrive. That is the swing, right? So that's why, if you use a very large current, there's a issue there, right? So what can we do? Well, let's see if 12% of the count is going to be okay. So we have a loop filter here. Now the PLL is going to be a slight modification. So right now the simulation is running. So let's show you a PLL. So here there is a mesh 111, okay, which is being driven by 40 megahertz of reference, and I'm not putting in any kind of a phase noise on these sources. Right now this is ideal, right? Later on in phase noise simulations I will put a source with a phase noise here, but for now I'm just looking at locking characteristics. So there's a mesh 111 here, there is a 6-bit adder here, and so which adds the output of 3-bit output of the mesh 111 to the coarse count, okay? And then the output of the adder is fed to the multimodulus divider, which is run by a clock which is generated by a VCO, right? So now in this case it's a dual band fractional N. So for that I have a pin which says LH. So if it is L means if this pin is held low, then it will be in the range of 24.3 to 26.5, which we will see uh, soon after this discussion. And if it is H, then it is going to go from 26.3 to 28.5. So that the two bands are covered by using this L and H, L/H pin. Whether you hold it high or low, if you hold it low, you are in the lower band. If you hold it high, you are in the higher band, right? So that is there. The control voltage is common for both the VCOs, and then this divide is division by 8. So this is coming from the injection lock dividers, which is 3-bit injection lock divider divides by 8, and that basically from 2 VCOs is multiplexed using multiplexer here. So this L/H decides which VCO output is divided and passed on to the multimodulus divider, right? So there are 2 VCOs inside this. So let's see what are these VCOs. Okay, so here you see 2 VCOs. Okay, so one VCO is I'm calling 27A, other VCO I'm calling 27B. So this is for the lower band and this is for the higher band. And output of this, there are 4 outputs, because 2 differential outputs, right? 2 differential outputs are going to this mux. And what is this mux? This mux is nothing but 2 differential pairs. Either of them can be on, right? Depending on the switching controlled by L/H. So L/H, high or low, decides which differential pair is selected, right? And the input to the two differential pairs are the two outputs of the two VCOs. So either of the band can be selected by L/H. And then there is a resistive load here. So this is just a differential gain stage, right? And they are being controlled by two diode connected transistors over here, and two are separate. So each one can be individually switched off, right? So using this NMOS device here, right? So this is a very simple mux for the output. Okay, now going to the divide by. So basically injection lock dividers inside each VCO is dividing by 8, and the output is given to this mux, which is a single bit mux. It's not a differential mux, so it's a single ended mux. So I'm using two mux, right, for the two differential lines. One is coming from this VCO, other coming from this VCO, and I mux the output, which is divided by 8, to the output here, right? So this is very simple operation. Now I'll go into each one of them, which I have earlier also shown that they are, this is this kind of arrangement where here there is a VCO here. Okay, so this is a VCO core, cross-coupled transistors, uh, device as a varactor or variable capacitor, and then there are two inductors as load, right? So their output is given to injection lock divider over here, and they are powered by this wide swing cascode current mirror over here. This wide swing cascode current mirror can be switched off using these two devices. Sorry, these two devices. If the inputs are high, then these two lines are pulled down. That means that the current mirror is not working, and so the current is cut off to all to the VCO and the three injection lock dividers. So basically you are switching off the VCO. So the band which is not required is switched off. Again, this is done by the L/H line. So L/H line is going to turn off one of the VCOs depending on which band you choose, right? So these are the three injection lock dividers here, which are divided by 2, divided by 4 over here, divided by 8 over here, and then there is a level shifter here to be in the right range so that this PPCL NOT gate can work on it. So to have a right trip point, right? So that its output can be a square wave here. Okay, so this is a this is a VCO plus divide by 8 using injection lock dividers. And if I go out, I have got two VCOs, either can be switched, right? So it's a dual band fractional and PLL that way, right? Now if I go further out, the rest of the things are hooked up almost the same way as in the previous session. The divide by 8 goes to the multimodulus divider here, and this the maximum frequency it can buck up to is 5 gigahertz, and then this is dividing anywhere from 64 to 127. The output is given to PFD, and PFD is a zero dead zone PFD, and we have dealt this in the previous session. It gives out up down differential outputs, and then it gives out C bar for cutting off the switching transients from going out of the charge pump, right? So that's there, and this is a normal charge pump which we have discussed earlier, right? This is a current source. This is a current sink. These are nothing but wide swing cascode current mirrors with a high impedance, right? And then these are just the transmission cells, and the output transmission cell is for cutting out the switching transients when up and down basically, or both are on, right? So this is a zero dead zone. That's why you have to have this one. Okay, so coming out of the charge pump, okay, we have a loop filter here. The loop filter values are as per this calculation: 22 picofarad, 1.5, C3 is 1.5, C2 is 320, sorry, 326, which I put as 320. R2 is 1.5, R3 is 21. I have reduced this slightly. I made it 10K. Okay, basically this RC combination R3 C3 is for reducing the ripple. Now where the ripple is coming from is basically here there is a fraction, the mesh sigma delta, which is being 12.5% the count of the lowest course count, right? Because of that, you are going to see fluctuations, and you can control those swings using this capacitor. Now as per the computation I'm putting the cap, but you can slightly increase this capacitor by 30% to further reduce this excursion. So I'll show you what I mean. So right now there is a simulation which is going on, and you see over here, these are the fluctuations which are by the sigma delta. Now, if you increase the C3 beyond 1.5, almost by 40%, this is going to become smaller and smaller, right? Now, the simulation has already been done for 4.3 microseconds, right? And you can see this locking and this small jaggering. This is within the one count of the FREF. FREF is 40 megahertz. So basically, the fluctuation is within 40 megahertz. Now, let's calculate what is the resolution, right? So here, first of all, let's see what is the count. So we took 27.5, we divided by 8, and then we divided by 40. So we have a count of 85.9375. Now I am going to minus from this the lowest count of mesh. So I'm left with 21.9375, correct? And then, so keep this number 27, and then for the mesh, there is a base count of 3. So I'm left with 18.9375. Now 18 will go as a coarse count, 0.9375 will go as a fine count. So I will just subtract 18 first of all, and I'm left with 9375. So I'm going to multiply with 65536. Actually, it should be 35. Okay. So, but anyways, so this count is around 61,440. So keep that in mind. 61,440. 61,440. Actually, it should be 439. So this comes up as all this 4 ones followed by all zeros. So this has to be fed into fine feed of mesh 111 sigma delta modulator. So this is going as 111, 4 times 1, and then remainings are all 0. And this output feeds, and then this is the coarse count. The coarse count has to be 18. So let's see what that 18 is. Just go to calculator and just clear it and say 18. 18 is going to be 0, 1, 0, 0, 1, 0. Okay, so this is 0, 1, 0, 0, 1, 0. Right, so this is the coarse count. Right, so now let's see what is the resolution going to be. So we have decided what has to be fed in. So let's see what is the resolution. So let's go to the standard calculation. Okay, so finding the resolution. So 40 megahertz, right? Divided by 65536. Okay, so multiply, let's say, with 1000. Okay, so in kilohertz, it is going to be 0.61 kilohertz is the resolution. But then there is a pre-multiplier of 8. So you have to multiply with 8. Okay, so you should be in the range of 5 kilohertz. So the resolution should be 5 kilohertz on a final frequency. Okay, now to have this kind of accuracy, you have to run, how much long you have to run this is basically, let's do it in microseconds. So it will be 40 inverse. So that will be 0.025 microseconds for one cycle, and there will be 65536 cycles to get an average. So you have to run it for 1638 microseconds, which means 1.6 milliseconds. So basically, for one cycle of sigma delta, you have to run it for 1.6 milliseconds to get the exact 5 kilohertz resolution on the output. And before, anywhere before that, it is going to be pretty close, but it will not be exact. So right now, let's see how much simulation has been done. The simulation has been done of 4.3 microseconds. So let's update this, reload, and say all windows. Okay, so I'm seeing in 4 microseconds or 4.3 microseconds where my average is. So let this update. Okay, I will take a snapshot of this after I do this so that I can put it as a front picture on my this thing video. And I wish to do this. Okay, this is updated now up to 4.3, right? 4.3. So let's correct this DFT. Go to the calculator and do it for 4.3 microseconds. Okay, so 1.5 to 4.3 microseconds. So basically before 1.5 I am going to be far away because it's still trying to settle. And just say update, and let me get rid of this guy, the old guy. Okay, so here I have 27.517. So basically I'm at 27.517 gigahertz. So I'm basically 18 megahertz off. Okay, and this sigma delta will eventually get you to the exact 27.5, right? Only thing is this vehicles which you see here, this is because the 8 count of 8 is appreciable. It's like 12.5% of 64 or something like that. The only way to get rid of this is either you increase the number of bits on the MMFD so that it is a lower fraction, or you increase this cap value, right? The final cap value. So you will have a much smoother averaging out, right? So I hope you understand what I'm saying. And then, you will quickly reach the average value. So I'm going to take a snapshot of this, okay? And I want to also keep this in mind, okay? So basically, I'm going to do one by one all the projects in this booklet in short duration of time, okay? So, uh, so let me just do a snapshot of this, and then we'll move forward with the discussion. New. Okay. So this is the snapshot. And it's a file, save, and let's say call this as carband when PLL. Okay, so they want a fractional and carband PLL. That's what I'm designing. Save. Okay, so this is done. Now I'm going to stop this simulation because eventually it will settle down. So I'm going to stop this simulation. And I'm going to cancel all this. I don't want to save any of the stuff, and I'm done. So now I'm going to show you something else. I'm going to show you what this VCO is going to do. So I'll go to test VCO, go to the library, go to test VCO core, and I'm opening this. I'm just going to show you the tuning range of this VCO. It's a dual band, and how do I use it? So right now L/H is going to down. That means that this is going to be the lower band. So I'm expecting somewhere from 24 point something to 26 point something, right? And right now this control voltage is 0.4 volts. And just run this simulation, launch ADL, and here I am going to do analysis is transient. And so this is a VCO, right? So let's run it for 300 nanoseconds. Okay, and let's do this as conservative and go to options, and I'm going to skip DC, and I'm going to add a convergence aid to this, which is the initial condition on the startup circuit, which is 0 and 0. Right, fine. So this is the initial condition, and coming back here, outputs to be saved. I'm going to select on design. This is the output, this is the output, and this is the diff frequency, and this is the control voltage, correct? Now what else I have to do? Nothing. Okay, to make this faster, I'm going to go to high performance computing, this and this, and then go to simulation, add a multi-thread to this. Let's say I'm going to do 2 threads per core. Fine. So I'm ready for simulation. I just simulate this. Okay, so you have to bear with me. So I'm going to do 4 corners. For lower band, I'm going to do the two extremes. For higher band, I'm going to do the two extremes, right? So that will just show that I'm covering the entire band from 24.4, let's say, or 3 to 28.5. So this covers the entire 5G band, band, right? Okay. So what else do we need to talk about? Uh, it's pretty simple. Nothing special in designing a fractional, and now the layout is going to consume time. So what I'm anticipating is if I do 8 hours a day, probably in 20 days I can do the layout. So I can do a design in 3 days. I can do the layout in 20 days. So 23 days, that means one working month. So for one working month, I can do the entire project. Now, handing it to a professor for 3 years at the expense of 40 lakhs or 50 lakhs every year, so that makes 1.5 crore or close to something like 200k USD. So you are going to give a professor from IIT or ISC or whatever 200k USD to get a fractional end done over a period of 3 years. I'm trying to get a consultancy from them, and I'm given a same ready-made answer. But I can do it in 3 days, a conceptual design, and 20 days in layout. I can do the entire, critical section, EM, COSIM, and everything. I can do this in 23 days, which is one working month. So one working month versus 3 years of a professor in IIT, okay, with their PhD or MTech students or 3 RAs or whatever. So what I'm trying to say is this has been running for many years. And consultants like me who go on the individual level, okay, the first time I went there, it was 2007, okay, and from then I've been doing trainings with them, but no consultancy, because whenever it comes to consultancy, they say, how can we pay you, under what pretext? Now I'm aware that there are many companies to whom they outsource the development at whatever these companies demand. They pay and get it. But an indigenous consultant who can do this in 1 month is not acceptable. Okay, so let's see where we were. Uh, let's see if I'm recording it. Fine, I'm recording it. Okay, so let's see the simulations. It is finished here. I'm going to plot this output and see the output, this thing. So I'll go to this guy and say result, direct plot from main. Okay, and I'll choose this guy, and I'll choose this guy, and this is node 11 and 10, so I'll choose either of them. Go to the calculator, minus the node 10, Control C, minus Control V, and this is node 10. Okay, and select this and do a DFT on this. So I'm going to 52, let's say 50 nanoseconds. Let's say it takes some time to start up. Let's say it starts up in 5 nanoseconds, but let's say 50 nanoseconds, and up to the end of simulation 300 nanoseconds, I'm going to do a DFT of this, and I'm going to plot this. So that's a plot. I'm going to zoom into this. Okay, so I have zoomed in, and this is 24.37 gigahertz. So this is the lower band, L band, which is 24.37 gigahertz. Right, now let's see if the control voltage goes, 1600. Okay, so this is the higher side of the lower band, and just say check and save and say simulate. Okay, so I don't need this window, and I will, at the end, I'll plot this at the highest frequency, so as to make sure that my injection lock dividers are not goofing up. So I'll see whether I get the divide by 8. Okay, so another some time for this simulation. Okay, so I have nothing to speak on other than this thing. With the this is 24.37 gigahertz. Later, I am also going to switch these. So basically, these currents which you are putting, I'm putting right now as large currents over here. The VCO which is off, I'm going to switch off 3 of these current sources. So the drain out of this current is minimized, and probably you can put it in sleep mode because you can have an individual switch for the 2 VCOs. So basically, you can put the PLL into a standby mode. Switch off this the entire thing here, and similarly you can switch off the mesh, the divider, and everything, so that the static losses can be minimized during standby, right? So that can be done. Okay, let's see where we are. Okay, so bear with me uh, on this one. Maybe I can put you on pause, come back, but I don't want you to get the idea that I do something special here while I'm off, so I'll let it run. Hardly going to be a minute. Right, so the peak swing is 650 millivolts, right? So basically a differential swing peak to peak is 1.3 volts, right? Which can be given to a Gilbert cell mixer. So I have also done a 27 gigahertz complete transceiver with the digital phase shifter and attenuator, right? And so basically this is a PLL, but I have also done, and you can find this on YouTube. Okay, so if you go to my channel, okay, so that's my channel, and if I go to videos and you go to playlist, go to playlist, and there is a car band for 5G. Let's see. 5G communication car band in ADS is the same Siltara process. And what I do here is the entire transceiver design for the car band. Okay, so I'm using a VCO, but ultimately, sorry. Okay, so what I have shown here is I had the complete transmitter receiver with the VCO as the current source, but then you can put the entire PLL. Right, so let's skip this ad. Okay, and I have switched off the volume, but I have done the complete transceiver with a QAM input. And I have done bit error rate, EVM, and everything. So basically, the entire transceiver with digital attenuator phase shifters, right, for beamforming. So basically, this is the receive section. This is the receiver, right? And there are basically the I and Q channel mixers over here, and your VCO input is over here for quadrature generation. So now here there will be a PLL here. Okay, now if you go further, I would show you a transmitter also, and I have done the entire channel between transmitter and receiver, and then evaluated the EVM and ACPR. So basically, if you look into this series of 5G, which was a workshop which I ran for 5 days for free for the entire world, and there were lots of participants from other countries also. So what you are going to see here is the complete transmitter and receiver, and these are the specs. Okay, so okay. Let me show you exactly what this is. So there are digital phase shifters and actuators on transmit side as well as the receive side, you can see here. And that means that they can be used for beam forming and shaping. And this is the entire thing at 27 at your carbon, right? So this is a transmitter and there is a receiver at the bottom, right? Transmitter and receiver. And the thing is to do this transceiver in Cadence along with the PLL and just wrap up the chip, right? And also I'm going to do a, a, a gas 3 watt output on each of this. So basically if it is a 64 element array, they can see I can put out easily put out hundreds of kilowatts on this one. So this is the PA, which is in gallium arsenide, which can put out 3 watt in the same 24 gigahertz to 28 gigahertz band. So let me put this on pause and let's see what has happened on the other side. Let's see where we were. Here we are. Okay, so I think the simulation is complete. Let me just update it. Reload all windows. And let's look at this frequency. Now this frequency is 26.4 gigahertz. So I have gone from 24.4 gigahertz to 26.4 gigahertz on the lower band. Now another thing is I can change the band now. So I can choose this one and connect it to VDD. So I'll be in the higher band. So first of all, I'm going to simulate the high end because this is 1.6. So this should be output should be around 28.4 gigahertz. So just check and save and run the simulation again. And I'll continue what I was talking. Okay. So I was talking something over here. So here I have a car band uh, front end, LNA as well as a PA. And again, I went to those guys, okay, who these guys, okay. I went to these guys and showed them the PA, and they said do it through respond, right? So anyways, I had to go and negotiate with the local colleges here to give me a chance because I'm not a regular professor there, and because of that I cannot participate in their respond program. Either I have to live with the politics of the private colleges or government college, right? And then get paid nothing, and then do a project for these guys for free, right? So they don't understand beyond their policy. Okay, so I'm not a I have to be if I am an adjunct professor. There are additional responsibilities which I have to take care. Live with the politics of this college just to push the respond through for 3 years. You understand what kind how difficult it is for a private consultant to work with these people, and they don't understand this. Okay, they don't want the work to be done in a short time. They want this to go for 3 years before something is produced to the table. Okay, so now so this is already done 1 year back. Okay, this transceiver was done 1 year back. More than 1 year back I had done the carbon transceiver minus the PLL, and now I have completed the PLL and I'm going to put them together. Okay, so anyways, so let's bring it down. Let's see where the simulation is. So the problem is the bureaucracy, right? And I have learned that if you partner with some of the people who are retired from these organizations and have started a company, it'll be easier to get the projects. And there will be no standard reply how to pay you, right? Okay, by the way, I would recommend you, if you are really interested, okay, beyond this, let's talk about some more projects which I'm going to do, uh, you know, as a challenge to myself. Okay, so this is SAC. Okay, so there are a list of projects here. So I can do RF related and embedded related as well as VLSI related projects. Then this is the Bangalore center. Okay, I can do few projects out of this, and then there is one control unit. I can do few projects from here. It says remote sensing. Yeah, master control facility. I can do some of these projects. So what I am doing is I'm going to do these projects and put them online for free, right? And show them how much time it really takes to do it and what do they have in mind when they fund it. Okay, so let's go to our results. This is done. Okay, reload all windows. Now I have moved to 28.55 gigahertz. So that's the higher end on the higher band. Let's see the lower end on the higher band. So I have done the 4 cases here. So this is going to be 0.4 volts. Okay, check and save. Simulate again. So this is the last simulation you have to wait for. After that, I'll close this session, right? And I'll put this recording on YouTube and provide a link in the LinkedIn. Okay. So I'm going to do at least initially I'm going to do 8 projects out of this in the coming 2 months. And then remaining projects are embedded or VLSI or FPGA based or something like that. Those also I'm going to do, right? Whatever maximum a single person can do in a period of 2 to 3 months, I'm going to put them online on YouTube. And I am assuming I'm not violating any of their policy because this is a document which is available to the public domain, right? So I can do this, right? Okay. So this is the last simulation. This, by the way, is a 130 nanometer CMOS process. This is called Silterra. And this is like 8-layer process with the top layer thick metal of 4 micron. So the inductor Qs can be good. And I have put in the inductors with the appropriate losses in this design. Later on, I'm going to simulate each inductor and put the realistic losses and adjust the performance. Okay, so this is the idea on the layout. And the same thing, I have done it in IHP SIGE process because this one, Silterra, is not space qualified. So for onboard electronics, they need space qualification. So I have repeated this entire project in SIGE 130 nanometer IHP, which is space qualified. So I'm going to do in both. Almost done. Now the issue with the Indian technology is people who can do it, they have no chance to do it. They don't get money to do it. People who can't do it in short period of time, they can do it, of course, but not efficiently as it is done in the industry. It will be run like academic project, right? They would be rolling in money to do this, right? So let me okay. So now here this is 26.33. Okay, so I have covered the lower band as well as high band. So the lower band was from 24.37 to 26.4, and this is going from 26.33 to 28.55. So basically the entire band of 24.37 to 28.55 is covered by this PLL. and this is a dual band fractional and ELN. Oh, okay, fine. So I'm going to stop here. Thanks a lot. Thanks.